presenting a talk entitled Smaller Than a Breadbox, Classification at the Nanoscale.
Thank you all for making it out here for this workshop. I don't know if this is a good thing or a bad thing to say, but please take it as a good thing. I have not been bored once this entire workshop, and that is awesome. That is exactly what I want from a multi-day academic conference excursion. So what I want to do is hopefully not change that trend for anyone. My talk is called Smaller Than a Breadbox, and I should explain this title. So how many of you played 20 questions growing up? Okay. What's one of the first questions that you ask when you're playing 20 questions?
Is it edible?
Yeah, is it smaller than a breadbox? The reason you ask that is because figuring out the size of something goes a long way to telling you a lot of interesting information about that thing. Scale plays an incredibly important central role in classification, especially when the stuff that you're trying to classify is itself defined by a scale. And that's sort of the central premise and the motivation for this talk. It's actually one of the things that ended up on our board over here. What problems do time and scale present for classification yesterday? So I'm hoping that I can address at least that one, since Evan and I have done a very poor job of shutting everyone up long enough to answer the questions on the board, which I take to be just another indication of how unboring these past few days have been. Okay, so that's prefatory remarks 1. Prefatory remarks 2 have to do with where nanoscience comes from, where classification in nanoscience comes from the perspective of chemistry. We've heard some talks about chemical kinds, some talks about nanoscience classification yesterday. And over lunch yesterday, one of my graduate students told us a little bit about classification in philosophy of chemistry. So I just want to recall some of that and remind you first of our naive approach to microstructure in chemistry, which says elements are the things with a certain number of protons or a certain number of protons and neutrons. That's all that we care about. We call that the naive conception of microstructure. This is Saul Kripke. Saul Kripke was one of the proponents of this naive view of microstructure. This is the typographically naive notion of microstructure from the gentle people at XKCD. So I have a slightly less naive microstructure that I want to talk about. Let's take a case. Suppose I have a few billion gold atoms, right? What I want to know is what properties those things have. And what I want to show you right here is that determining the properties of that collection of a few billion atoms is much more than what the naive view tells us, much more than just looking at the nuclear charge of all of those atoms and making an inference on the collection on that basis. So we could have, most of us think about macroscopic lumps of gold. And our macroscopic properties, well, the gold is mostly inert, it's shiny, it's yellow, it's malleable, it's ductile, it melts around 1064 C. Because it's a metal, it has delocalized electrons. We could have gold nanoparticles, so I showed you guys some of those yesterday in my little vials that I held up. Those are going to be catalytically active in opposition to this mostly inert, right? They're going to be red-brown in solution or brown dust if you dry them out as a collection. They're not really going to have color in the normal sense that we think of color as individuals. So one of the things that I can't remember if it was John or Evan was talking about yesterday was this idea of, do we classify nanoparticles as an individual object or as a collection? Was that you? Me. That was you. Okay. They said it was so exciting. It all blurred together. So we have differences in color. We have some properties of nanoparticles that we just don't see at the macro scale. They're plasma inactive. They're capped with surfactants. We're going to come back to that later on. They're brittle as opposed to malleable and ductile. They are single crystalline or small polycrystalline as opposed to sort of large delocalized electron centers that we think of as characteristic of metals. we could have a third case, too. We could have a collection of a billion atoms that just has the properties of the billion atoms, right? It just has the electrons that we associate with an individual gold atom, so 79 electrons around each nuclear center. This xenon 5d10 electron configuration. And this is mostly a theoretical construct, right? This is not a way that we find gold atoms in the universe, except in very strange situations. So if we expand beyond our naive conception of microstructure, we find that we can't just associate a set of properties with nuclear charge and be done with our story. So that's sort of where I want to start with some of these things. Oh yeah, and I just have pictures of the gold nanoparticles zoomed in. This is our 500 nanometer scale bar, just so you can see them. So what I want to say is that we get an explanatory asymmetry between microstructure and macroscopic properties, where we see structure explaining properties. I can actually tell you stories in each of those individual cases about why our macroscopic lump of gold is shiny and yellow and inert, and why our nanoparticles are reddish and plasma inactive, and why they have to be capped with surfactants, and why our individual gold atoms would have the electronic configuration and the electronic symmetries that they have. The macroscopic and electronic properties differ depending on the arrangement of these atoms. They're not the same from one another, but it's always going to be a structural story that gets us both the individual sets of properties and the relationships and differences between them. That said, the atomic identity, the 79 protons in the nucleus, underdetermines these chemical and physical properties that we're interested in. So this is all sort of background. It's a paper that I wrote a couple years ago that you can read on your own time. And as background, I want to say that's how I think about chemical kinds. I also happen to think it's the correct way to think about chemical kinds because it's the way I think about chemical kinds, and I'm a philosopher, so I like to think things that I think are correct. So that's by way of preface 2. This is how I'm coming at this problem. And what I want to do now is turn to first to a little bit of philosophy of science and talk about why we might care about kinds as philosophers, or as people who sometimes sit in rooms with philosophers. And then talk about this thing called the structure-property paradigm, which I take to be a generalization of this association between microstructure and properties that I just showed you in the case of gold. And then I'm going to take all of that and apply it to some classificatory questions in nanomaterials, and finish out by talking about 2 of the most interesting concepts that I find in nanomaterials from a philosophical perspective, which are the concepts of surfaces and the concepts of alloys. And that, I should just flag here, the alloys conversation is actually going to get picked up by the next talk, by Michael's talk. So that's how we're going to do it. Let's get started. For real this time. So I take it that we could have at least 3 different kinds of problems that we might care about when we care about kinds. One, and this is a very classical metaphysical problem of kinds, what are kinds? What sorts of things are they? How do they exist in nature? So when we had my graduate student Chris standing up here yesterday, he told you Plato sat around and thought about this question and said, well, we have to have some sort of form, some sort of perfect world that gives us the essence of the individuals in this world, that relates them to one another, that makes them all the same kind of thing. And then we got a lot of stories about mutilated dogs. So that's the metaphysical problem of kind. What sort of a thing makes a kind the kind of thing it is? I like to think of this as the question of kind essences, but obviously if you care about the metaphysics of kinds, there are many more questions than just essences. There's the reference problem. This is actually the problem that guy Kripke in the big floppy hat was worried about. And this is how do we manage to get our kind terms to refer? When I use a piece of language, for instance, stem cell or embryo, how do I know that when I say embryo, I mean the same thing as when Ubaka says embryo, as when the Supreme Court of the United States says embryo? And this question of how are linguistic associations of, say, properties or of, people will answer it in terms of causal histories of these kinds, manage to come about in the production of language is one that has troubled philosophers throughout the ages. So we have, this gets associated with theories of concepts, with theories of, do I make sense of my words by associating properties with them or by associating causal histories with them? I actually think it's really interesting to think about this in the legal context, because the legal context gives us a combination of very defined property-driven definitions of things that then have causal histories of their own built into the notion of precedence and case law. I had never thought about it before, but those were like the furious notes that I was scribbling during your talk. And then, of course, the sort of classical philosophical problem of projectability. If I use a word, how do I know that I can use the word in the same way in the future to pick out the same sort of thing? If I point to my dog Linus on this screen and then I get home and there's a furry red and white object that's running at me, looking at his food dish, how do I know that that is actually Linus, right? So those are two of the classic problems of kinds in the philosophical literature. But there's a third problem, which I'm going to call the methodological problem. And it's how do we use these things called kinds? What do we use them for? How do we know when we use them successfully? What are our conditions for success and failure? How do we rationalize the success of classificatory practices in science and in everyday use? So this looks at the longevity of individual concepts like gravity, or the death of concepts like phlogiston, and things like hardness as well. So I'm not gonna give you this argument here, but I've made this argument elsewhere that insofar as philosophers of science should worry about natural kinds, what they should worry about is the methodological problem. This problem, again, is the problem of rationalizing, confirming, and projecting both our taxonomy, our sort of hierarchy of kinds, and our individual classificatory practices. And then being able to license inferences from theoretical terms. So this is a problem for the sort of reference problem of kinds that comes out from the methodological problem. And then locating relations between kinds and scientific theories, whether or not we want our kinds to be the stuff of theories, the stuff that theories are about, or whether we want kinds to be just a stopgap on the way to actual quantified mathematical scientific laws. And then how do we explain the success of things like cross-cutting? So cross-cutting is the ability of a kind to fit into multiple non-mutually exclusive taxonomies or methods of classification. So I could think about, let's see. Yeah, well, I need something that's a poison. Arsenic. Arsenic is both a chemical and a poison. And now I can only think of old lace. Someone give me hemlock. Hemlock is both a plant and a poison, right? So poison cross-cuts vegetable and chemical. So we have all of these questions that come out of the methodological problem in the context of philosophy of science. I can give you a couple examples of philosophers who have thought in some detail about individual kind concepts and how they come about over the course of scientific history. One, we actually heard this in Vadim's talk yesterday, Hasek Chang's investigations on temperature in his book Inventing Temperature, and he does similar things with water, acid, and chlorine now. So these investigations rationalize the evolution of a concept in scientific and everyday practice. And he has this theory of epistemic iteration that's supposed to explain to us how we get this concept and how we manage to use this concept over and over, how this concept picks out a relevant scientific kind, excuse me. And then Mark Wilson has a theory facade account of how concepts engage with scientific theories that explains the movement. He calls this the movement of classificatory concepts like color and hardness and weight across different theoretical frameworks. So hardness in wood, hardness in metal, weight in space, weight on Earth, weight on Mars, color as it applies to, well, not really quarks because that's just a complicated analogy anyway, but color as it applies to nanomaterials, as it applies to dyes, as it applies to human eyeballs. So here, if you have spent any time reading philosophy and you've encountered Mark Wilson, you will know that this is sort of the characteristic terseness of the man. Don't worry, this is part 1 of 2. So I'm just gonna read it in full because there's no way around it at this point. This is Wilson talking about hardness in his book Wandering Significance. He says, in everyday context, we adjudicate the hardnesses of various materials, both comparatively and absolutely, through a wide variety of comparatively easy to apply tests. We might squeeze the material or indent it with a hammer, attempt to scratch it or rap upon it, and so on. In most cases, we'll be scarcely aware of the exact technique we will have employed for this appraisal. Did I rap, squeeze, or scratch that piece of wood? I can't really remember. In fact, our choice of tests is likely to have been suggested by the material in question. We instinctively appraise a wood by rapping upon it, a rubber by squeezing, a metal by attempting to make a small imprint, a glass or ceramic by rapping lightly or scratching, as opposed to by trying to make a small imprint. You're not going to stick a needle into a ceramic to try and figure out how hard it is. In fact, we are normally interested in comparing hardnesses mainly within natural groupings of stuff of generally allied characteristics. Metals with metals, ceramics with ceramics, and so forth, although interesting crossover cases can arise. So what you should notice here, these bolded words, he's saying the way that we go about interacting with materials drives these things into kinds that we can then investigate operationally, right? And so he goes on in characteristic Mark Wilson fashion. I should mention this is page 338 of a 660-page book, all about this exact subject of how our concepts manage to arise and develop through theoretical frameworks. So he says, our employment of hardness silently distributes itself into a patchwork of sheets, locally distinguished by a certain vein of probing, be it scratching or tapping, that sit over various varieties of material stuffs and continue smoothly into one another. As an inferential tool, most of us employ the term hardness informally as a generic single-scale folk physics parameter that we will consult in selecting a material for, e.g., manufacturing purposes. Left at this general level, the term requires further specialization before it can carry much data usefully. So notice we're getting the story of the relationship between the scientific practice, the tapping, the scratching, the testing, the sorting, the classifying, and then the using of the term that picks out that associated property. Accordingly, he says, over each localized domain of related stuffs, the hardness parameter is likely to silently specialize on the forms of probing that prove most informative with respect to the materials and purposes locally at issue. So you don't have to agree with this. You just have to notice that he's saying go to the theory. The theory is going to constrain the ways that we think about how to solve the problem of classifying and understanding this material property. Okay, so now I want to talk about how theories are going to constrain the ways that we classify material properties in chemistry and nanoscience. You already saw a little bit in chemistry, and just to remind you, we looked at this case of gold and how the microstructure of gold constrains but doesn't totally determine the way that gold itself presents in terms of its macroscopic properties. If we think of microstructure in the naive way, right? If we think of microstructure in a more complicated, messy way, we might be able to recover some of those properties in terms of the larger scale molecular geometry of a piece of gold, right? So a few things to note about chemical kinds. The properties that are of interest to chemists range across a variety of scales. We're interested in bond angles. We're interested in yields of industrial scale reactions. We're interested in everything in between. Macroscopic kinds such as bulk gold license inferences about macroscopic properties, right? My bulk lump of gold can be malleable, can be ductile, can have macroscopic weight, can be yellow. My gold nanoparticles aren't the sorts of things to which those terms apply. It doesn't make sense to talk about things like orbital symmetries, atomic properties of macroscopic gold, nor the melting point of an atom. So this is where we see scale start to enter again, right? This idea that the properties that we're interested in are actually going to index themselves to individual scales. I call that scale dependence. And I actually can't remember if that's going to come up again because I made some of these slides over lunch just now. So we'll find out. But the case studies we just looked at with Wilson and Chang can aid our understanding of this explanatory and confirmatory movement across scales, right? So Wilson's story about how we test different materials differently to pick out the hardness is going to help us understand why certain sorts of properties are going to be available in certain settings and not others. What I'm going to add into that is the idea that certain sorts of settings are going to be carved out and themselves differentiated from one another by the scale at which you're investigating the material. Generalizations may be available depending on one's metaphysical predispositions, and we're not going to say any more about that right now. So this thing, the structure property paradigm, this is a generalization of what I introduced earlier, this explanatory asymmetry between structure and properties in chemistry. And the most basic version is that changes in properties necessarily correlate with changes in structure. No surprise there, right? If I have a metal that changes all of its properties and nothing about its structure changes, I have weird alien metal. That's not how materials behave. I need changes in structure to explain changes in properties, whether or not I want to make deep metaphysical claims about the essence of that thing being located in the microstructure or in the properties or somewhere in between. All of my properties that I'm interested in are explicable by structure, and it's structures that we seek out as chemists in order to understand the properties that we're interested in better. Properties themselves are manipulatable by manipulating structure, so I could think about breaking bonds, changing bond geometries in order to obtain new properties in my materials. If I take a piece of diamond and I think about, conceptually in my mind, rearranging all of the bonds in that diamond into hexagons, that's how I get to graphite, is by changing the structure to change the properties, to change the identity of the thing. And the failure of this correlation indicates that I've done something wrong in my science, right? I have a poor experiment or a misunderstood experimental setting. It doesn't tend to indicate that there's a failure of the structure property paradigm. It tends to indicate that there's a failure of the application of that to a particular setting. So there are philosophical arguments defending the structure property paradigm that you can find in Robin Hendry and Mark Goodwin. Citations down there.
Can you define two words for me, the word structure and the word
property? So I take structure to mean a complicated version of microstructure that includes molecular geometry. So any of my features of a material that have to do with the relationship between atomic centers, which could be bond energy, distances, angles, ionization, whether it's a polar bond, nonpolar bond, whether it's an ionic or covalent bond.
by chemical, you mean the individual molecule,
No.
as opposed to the chemicals in the bar of gold?
No, it could be either. So what I was trying to show in the previous slide is that the properties that we're interested in chemistry could be microstructural properties, could be macroscopic properties. But even if I'm thinking about something like melting point or enthalpy of formation, right, I'm going to have a microstructural story for where that comes from. Okay, so philosophical arguments exist out there in the world. I'm going to give you the Google Scholar argument, the infallible. I typed this into Google Scholar, and here are some numbers that I got. If you look for the bigram structure property, these words stuck together in that order, you get it in over 80,000 scholarly texts published since the year 2000. So some people will talk about the structure property relationship. Some people will talk about the structure property paradigm. Some people will talk about structure property correlations. And just for comparison, if you do the same thing with natural kind, you get about 14,000, right? So this is a very common set of correlated terms out there in the literature. But we should not rely solely on Google Scholar. So let's look examples from the history of chemistry. The discovery of fixed airs, the idea that you can isolate the identity, the structural identity of gas, gives rise to explanations about well, they use it to confirm theories. They happen to be conflicting theories, but they use this to confirm theories about the actions of gaseous principles. Dalton's law of constant and multiple proportions picks out structural features of relationships among chemicals. Kekulé's ring structure of benzene led to a unification of 19th century chemists' understanding of aromatic compounds. The contemporary periodic table of elements contains microstructural and macrostructural information, but we tend to think of the elements as the things with a certain amount of protons in the nucleus, right? We order the table, the whole structure of the table is based on microstructure, even though we'll associate that with macrostructural information. And we have textbook representations of organic reaction cycles, such as the Krebs cycle, which depict things like macroscopic interventions. I can add water here, subtract water there, performed on individual molecules, which is just a weird scale conflation that is all over the place in chemistry, right? You can add molecules or add macroscopic. One of the ones that I love is like when you add heat to a molecule to create change somewhere, right? It's not that we're adding heat to an individual molecule ever, it's that we're adding heat to a group of things and we expect that to perform collective action on the component molecules. But it's the story about the behavior and the structure of the component molecules that we're after when we perform that macroscopic intervention. Okay, so that's what I have in mind when I say structure property paradigm. And now what I want to show you is that the structure property paradigm as it exists for chemical kinds is insufficient to explain the kinds that we're interested in nanoscience. So the kinds of structure that we're interested in for chemistry have to do with sort of reliable, repeatable, identifiable compositions of atoms in the same relationships to one another. Every molecule of caffeine is going to have approximately this relationship of atoms in it, right? Not every gold nanoparticle, even if I say they're all 20 nanometers, and even if I say they're all capped with sodium citrate, and even if I say that they are, you know, extraordinarily monodispersed, they're not all going to have exactly the same number of atoms in them. Even if they happen to have all the exact same number of atoms in them, they're going to be in slightly different relationships to one another. It's not going to be totally monocrystalline and totally rigid and repeatable at 20 nanometers. We're going to see some examples of assuming the opposite for theoretical purposes in the next talk, which are exciting. Because, I mean, part of what's really exciting about this is that we're running up against exactly the limits of the chemical conception of stuff as this sort of reliable, repeatable, every instance is going to be exactly the same as the next instance. Okay, so this is, actually I don't know the origin of this diagram, but we use it all the time in our lab. That nanoparticle physical and chemical properties come to us from a combination of four things: the composition, the size, the shape, and the surface chemistry. Composition is what we care about in regular old chemistry, right? Composition here taken to include complicated features about bond angles, bond lengths, bond energies, that sort of thing. And what I'm going to show in the next section is that we actually care about composition some, but in a lot of cases not as much as size, shape, and surface chemistry especially. Before we do that, just in case you have forgotten everything we talked about yesterday, because we've been talking about stem cells all morning, the nanoscale, somewhere around 1 to 100 nanometers. I think this came up in Evan's talk yesterday, this question of how do we actually define the nanoscale as about 1 to 100 nanometers. I've seen people get out of this by defining it functionally. So this was the question of whether we take proteins to be nanomaterials yesterday. Proteins exist at the nanoscale, 1 to 100 nanometers. We typically don't think of them as nanomaterials because they don't do the thing that we want our nanomaterials to do. Anyway, So the thing that we want our nanomaterials to do is to take advantage of being nanoscale. We want them to exhibit features that we don't see in macroscopic materials and that we don't see in individual molecules. Things like surface plasmon resonance, things like quantum confinement, things like turning gold into a catalyst, which is crazy talk, right? The reason that some of you have gold on your fingers as your jewelry metal is because it's super inert and not catalytic. But once you shrink it down to the nanoscale, gold's a catalyst. Yeah.
So it only has properties that are subjective and that could change as a function of time depending on what you're looking for. Would you not start classifying and reclassifying nanomaterials? This is a nanomaterial or it's not a nanomaterial because it either does or does not exhibit.
Like when it's not exhibiting, like if I'm not shining a laser on it at this exact moment.
We'll just say that for now, we don't think it's an important nanoparticle. It's of the right size and dimensions, but it doesn't exhibit the behavior we're looking for. But later, we find that, wow, you put it in the microwave and all of a sudden it does this really strange, fantastic stuff. And now we say, oh, now this is nanomaterial. Or later we say, oh, no, that was an error, and now we disclassify it as nanomaterial.
Yeah, I'm okay with that. You seem like you don't want to be okay with that.
No, I don't want to be okay with that. Because every time you reclassify something, it requires usually some type of human intervention. And that thrashing of knowledge, so to speak, is problematic for many reasons.
So I mean, I guess this is where some of the conversations in this workshop will be helpful here. So
so if you have a stable definition that might be able to be specific enough so that you don't have to classify or reclassify something, that may be very helpful.
So would you rather include proteins then, because they happen to be at the nanoscale, or exclude them because they're biological?
I'm fine with this, and some people will, but I don't. I'm more practical. I think that you can classify as nanomaterial if it fits your definition. If it doesn't, then don't.
Okay.
And it's really that straightforward. But don't classify it and unclassify it and go back and forth between the two as new discoveries or changes happen.
So I guess I don't see.
So for instance, there's aluminum.
Hold on, let me phone a friend. No, I guess I don't see it as a matter of I've made something and then it happens not to exhibit nanoscale like properties that I'm interested in, and so I'm gonna call it not a nanomaterial. I think part of what's interesting about all of this is that most, I mean, with the exception of like peacock feathers, right? The nanomaterials that we're interested in are artificial. We have an intent to make something with nanoscale features before we start making it.
So imagine things like planets. They reclassify Pluto as something else other than a planet, which got a lot of people who were learned about 9 planets, and now we have these other things that are not planets that we once thought as planets. It's kind of it causes confusion for them, and so if one was able to have a stable definition, and as long as the definition for what is a planet now remains stable, then that's okay, and then it just simply is advancement of science. But if people were going back and then reclassifying it as a planet, and then it's not a planet, is a planet, not a planet, you can imagine, all the kids around the world thinking, there's 8 or 9 planets, is then how they would speak of this, because we don't know what to do.
Yeah. Well, okay, so I understand the worry. I'm going to say 2 things, and then I'm going to move on with the talk. Thing number 1, all of those kids who are walking around with this disjunctive definition in their heads of 8 or 9 planets are still going to be able to tell you that after Uranus comes Neptune, and after Neptune comes Pluto, except for those weird times when Uranus is outside Neptune, right? Doesn't that happen sometimes? He has an incredibly eccentric orbit, right? Yeah. So I think, they might be confused about what some scientists up in their giant telescope rooms are calling things, but they're still going to be able to tell you what's out there by naming the individuals. So obviously, I care about being able to call something a planet because I'm throwing an entire 2-day workshop about how we classify things. So the second half of the response there is that there's this guy called Otto Neurath, who is a philosopher in the 1920s, 30s in Vienna. He has this famous analogy. It's drawn from another philosopher's thing because no philosopher ever works in isolation. It's drawn from the ship of Theseus, but we call this Neurath's boat. It's a very famous thought experiment in the history of philosophy of science, which goes something like this. Science is a ship. It's a ship that is at sea, that is constantly leaking, constantly on the verge of sinking, that is made up of individual planks of theory and experiment and evidence. And every time we do an experiment and something breaks, we get another hole in our ship. And we have to rebuild this ship every day, constantly. But we can't go back to shore and start all over again and get a new ship because we're stuck in the middle of the ocean. We have to rebuild the ship at sea. So it's not that we can just throw out all of our classification systems that we already have, or that we can throw out the evidence that we have, even if it's messy. This is what the world has given us, such as it is. This is what we have to work with. So I'm inclined to say that because of the actual history of interest in nanomaterials, this idea that, you know, when Smalley made the buckyball in '85, he said, 85? 84? 85? I think 85. I should know this. I graduated from Rice. I feel like it was like a condition of admittance. Anyway, when Smalley made the buckyball in the middle of the 80s, he made it because he was interested in manipulating features of that kind of material that he couldn't get from macroscopic materials, right? He was interested in what happened to the material differently at the nanoscale that we don't get at the macroscopic scale. And so that idea that there's either some human intention behind the making of these things or some difference in function or properties seems to me at least an implicit part of why we care about the nanoscale at all. And so I'm inclined to let it into our classificatory definitions of what counts as a nanomaterial, because historically that's where it comes from.
I'm going to ask us to put a pin in reclassification, which seems to be a really important, unless, John, you want to?
I was going to say, there are many nanomaterials that are not manufactured, that just occur naturally. Like when you make soup, that virtually all the nutrition is passed to you on a nanoscale, and pigments and many other.
Right, but we don't call soup nanomaterials. That's actually kind of the
obviously
point
you've
here.
never talked to a food scientist. They're extremely adamant that they're nanomaterials in naturally occurring in food, and that they should, because of that, regulators should not say that having nanomaterials in food is bad because they already occur.
So is that different than the people who say we shouldn't have chemicals in our food?
Well, I don't know whether any regulators are saying you can't have chemicals in food, but I know, for example, in France, you label nanomaterials in food, which is nonsensical. And
right, and it's nonsense, right?
Right, but it happens.
Well, there are lots of organisms that depend on nanomaterials, like chameleons and butterflies.
And they're
But
in
your point is
biology,
what
they're
we call a nanomaterial.
Yeah.
Not, there's nanomaterials in other things. You want
Right.
to say something is or isn't a nanomaterial.
Yeah.
And like the equation of, so that, and.
Yeah, and so I'm okay with things like chameleons and butterfly wings and peacock feathers, which are they're nanostructured features that give rise to optical phenomena that are a consequence of the scale of the structural features.
Which is different than saying the peacock feather is a nanomaterial.
Right.
What?
Well, it's saying it's a nanostructured material, or it has nanostructure. But I guess I'm not super familiar with the arguments about there being nanomaterials in soup.
Why don't you continue this, because I think these questions are going to come back over and over again.
Right.
So.
Okay. I just want to make sure the person who came in, so our last speaker is supposed to come in around 2. I don't know if it's around 2 now, but okay. I don't think that was him, but it's possible. Yeah, let's just leave it open in case. Who could tell us about nanomaterials? I mean, he's gonna tell us about nanomaterials and drug delivery. That's a different story, but not so different. Where was I? Oh yeah, okay, so I like to define the nanoscale functionally. People in the second row here disagree with me. We can have that conversation in a lot more detail a little bit later on. But you know, the function comes as a result of the size, and we can all at least agree that the nanoscale is about 1 to 100 nanometers. And I like to use the function to get out of the squishiness of the about 1 to 100 nanometers. But obviously it introduces other sorts of squishiness, so we'll talk about that later. Other interesting features of nanoscale materials, you get changes in chemical properties relative to macroscopic materials, changes in reactivity, changes in hydrophobicity, hydrophilicity, new physical properties, things like plasmon resonance and quantum confinement, and then changes in physical properties, so changes in color, changes in conductivity, changes in hardness, so on and so forth. And right, so before I move on here, just to make it clear what I'm doing, I'm going to argue that each of these 4 things is essential to classification in nanomaterials, whereas for regular old chemical materials, it's really just composition that people care about. So composition, what is it? It's the chemical makeup of the thing, whether it's made of gold, whether it's made of carbon or silicon, whether it's titanium deposited on a silicon wafer. The elemental identities and the proportions, be they standard chemical atomistic proportions or much more often, especially in the metal nanomaterials that I look at, you know, mushier proportions. This is an alloy. This is a single metal that's about 30 nanometers. Whether there are crystal structures, whether it's polycrystalline, monocrystalline, what sort of lattice spacings we're working with, what sorts of impurities we might have in our samples. And then I'm throwing in here as a parenthetical solvent identity. So this is something that matters for many purposes, especially with nanomaterials that you want to put in your body. You want it to be in a solvent that is not toxic to human beings, assuming you're a human being. Just checking. So I think we might be interested in that as an element of chemical composition when we're thinking about classification of nanomaterials. But typically, the way that you see these things, it's going to be, you know, gold nanomaterials, gold nanoparticles that are capped with CTAB, or gold nanoparticles that are capped with sodium citrate, where the active part of the material is separated from both the cap and then the solvent that you put those things in. So usually solvent identity is going to be a sort of necessary feature of the story of how you get to the nanomaterial, but it's often distinct from the identity that you assign to the nanomaterial. So it's relevant to classification, but perhaps not relevant to the identity of the material. And that's kind of an interesting distinction that I think you get out of looking at nanomaterials. So beyond composition, we have dimensionality and shape, and I'm going to apologize. Some of this is repeating what we saw yesterday. The way that dimensionality works, the question is how many dimensions are above the nanoscale. This is a little bit counterintuitive. So your 0D nanomaterials have 0 dimensions above the nanoscale. Every dimension is at the nanoscale. So your balls, your buckyballs, your spheres, your cubes, your things like atomic cars and guitars, which a guy named Jim Tour at Rice University really likes building in his spare time. You have 1D materials, which have 1 dimension above the nanoscale. If you think about that, it's really small in 2 directions. That means there's 1 direction where it's really long. Therefore, you get things like wires and belts and tubes, carbon nanotubes, 1-dimensional. 2-dimensional is a little bit easier. It's just thin films, right? And then there's this sort of special subcategory of zero-dimensional materials called nanoclusters. We're going to hear more about that in a little bit. Nanoclusters are extra small nanomaterials, around 1 to 10 nanometers. And we often think of these as somewhat more molecular, more like chemicals in their structural features than larger nanomaterials. So buckyballs, the sort of classic first nanomaterial, carbon-60 has exactly 60 atoms every time until you start throwing more atoms in the middle of it or extending it out and then changing the geometry in reliable, repeatable ways. That's a molecule, right? Our 20 nanometer gold spheres are not molecules in the same way. So just something to keep in mind, especially as we move to our next talk. So in addition to composition and dimensionality and shape, we care about surface chemistry. And John told us yesterday, and I think Evan reiterated it a bit, surfaces are really messy and complicated, and we don't understand them that well. We don't have anything like the periodic table of surfaces. Surfaces interact in very complicated ways with both the solvent of the material and the material that is on the inside of the surface. So the interior of the nanomaterial, the exterior, the interface. And we can ask a lot of questions about surface chemistry when we're interested in nanomaterials classification. So things about the identity of what is on the surface, whether it's the same thing as the interior of the material, whether it's capped with an additional surfactant or reagent, so the arrangement of those surfactants, the arrangement of the surface, whether it's the same as the arrangement of the interior of the material, concentration of any surfactants that are on there. So I tend to say surfactant and capping agent interchangeably. You guys may have problems with that. Please have problems with it quietly to yourself for the rest of this talk. Surfactants or capping agents in metal nanomaterials you can think of them like sausage casings on the outside of the nanomaterial. Nanomaterials don't want to be nanomaterials. They want to either dissolve into atoms or agglomerate into macroscopic materials. Surfactants, capping agents are the things that keep them at the nanoscale, especially for metals. And you can get similar effects to the capping agent effects from things like surface restructuring or electrostatic stabilization. So you might worry when you're asking about the surface chemistry of material, you might worry about the orientation of the cap. So in this picture here, we have a sort of medium chain hydrocarbon capping a gold surface. If all of these hydrocarbons were laying flat, or if they were tangled with one another, or if they were perfectly perpendicular, you would get different properties of the material that would be affected from the structure of the surface, right? So we're still seeing the structure property paradigm at play here. So things like spacing, concentration, and dispersion of these capping agents as well, and then intermolecular forces among caps is something that our group has worried about in the past, and also, again, solvent identity, right? Okay, so I've just told you about how important surfaces are, and what I want to do is take a little bit of time now to tell you why surfaces are so important at the nanoscale and why this is an interesting philosophical problem. So the role of surfaces in nanomaterials differs from the role of surfaces in macroscopic materials, and it differs in at least 3 ways. I'm going to tell you about those 3 ways after I explain this picture, which to me is the most interesting picture of nanomaterials. It may not be the most interesting picture to you yet, but it will be in approximately 30 seconds. Here's what's so interesting. At the macro scale, the scale of nuts and bolts and glasses and lunches and philosophy talks, basically, effectively, none of the atoms in any material are on a surface proportionally, right? I say basically and effectively because there's at least one person in this room who did an undergraduate degree in math, and we know that it's not actually infinitesimal from a mathematician's standpoint, but effectively infinitesimal, even down to 63 micrometers, which is maybe about a quarter of the width of a human hair. effectively, none of the atoms in a material of that size are on the surface. The reason is that atoms are very, very small. When atoms get together in very, very small arrangements, like this arrangement of caffeine, my favorite molecule, apparently, there's not really any part of this material that is a surface, or all of the material is the surface, right? There's not an outside and inside that we can distinguish from one another and say the outside is behaving differently from the inside, or we can see the outside as a part of the material in a way that we can't see the inside as a part of the material. But at the nanoscale, you can have 35 or 45 or 75% of the atoms on the surface. You can still have a surface. There's still a difference between the stuff that's on the outside and the stuff that's on the inside, but that surface is no longer effectively infinitesimal. It's making up a significant fraction of the material. And that's exactly what makes nanoscale functionality, what makes a lot of these properties and behaviors of nanomaterials that we've been looking at, the sorts of properties and behaviors they are. That's where nanomaterials gets a lot of its properties and behaviors, things like quantum confinement and plasmon resonance. So these structural changes, nanoscale surfaces are not effectively infinitesimal. This gives rise to novel phenomena, which we call behavioral changes. It also imposes additional constraints. This is what I was just talking about the role of surfaces for, or the role of stabilization for nanoscale surfaces. So surfaces are higher energy than the interiors of materials, which is not a problem when basically none of your atoms are on the surface. It's a huge problem when 25 or 75% of your atoms are on the surface because, again, those atoms, higher energy, less stable, they want to fly apart or collect more material so that more of the atoms are on the inside. Keeping them at the nanoscale requires that sort of external stabilization. So what surfaces are doing at the nanoscale is very different than what they're doing in macroscopic materials and different from any sort of surface concept that you might see in molecular materials. It might be worth flagging here. You can still think about things like electronic surfaces or potential surfaces in molecular materials, but that's not actually surfaces as a material boundary between things. That's sort of a conceptual or theoretical structure that's associated with a mathematical surface. Different thing. Okay, so here are some pretty pictures to convince you that I am right. So this is a mathematical model, and this is a TEM image of a palladium dodecahedron cluster. This cluster, in its ideal form here, would have 3,871 atoms, of which 1,002 would be on the surface. And that's approximately 26% of the atoms on the surface of the material. Over on the right here, we have, this is a metamaterial that's built up of short carbon nanotubes stuck together in a lattice with sheets of graphene. And you can see there's a sense in which all of the atoms in that material are on the surface. But there's still a surface to be seen. So this is the difference in structural role of surfaces, right? They're not effectively infinitesimal. Differences in behaviors, I've alluded to this a little bit with the structural color that you get out of peacock wings and butterfly. Peacock feathers and butterfly wings, that's the one. These changes in scale drive the differences in surface functionality that we're interested in. So we get, I like to classify this into two sorts of interesting new properties. One is novel phenomena that come as a result of the scale, and these are usually things that are treading the line between classical and quantum phenomena in kind of cool ways that I bet Michael is maybe going to talk about. Michael's not going to talk about. Like things like localized surface plasmon resonance and quantum confinement, which is responsible for at least some old stained glass. This is actually, this is Gaudi, that's late 19th, early 20th century, so probably too new for some of that stained glass. But it's my favorite picture of a stained glass window, so I'm leaving it up there. And then you get changes in behavior, things like increased catalytic activity, changes in conductivity. So these are things that you could measure that property in a macroscopic material. You can measure the conductivity or the catalytic activity of macroscopic gold, but you're going to get a different measurement at the nanoscale than you are at the macro scale. Okay, and the problem of stabilization, I've done this a bit already. Surface atoms less stable than interior atoms. Nanomaterials require surface stabilization. I should flag here metal materials, carbon nanomaterials, and molecular. They typically can hang out without external stabilization. Okay, so that's what's going on with the different role of surfaces in nanomaterials relative to macroscopic materials. And when I'm talking to rooms full of philosophers, I argue that this makes surface a scale-dependent concept and makes the role of surfaces, the way we understand surfaces, dependent on some of the assumptions that we're making about the role of the surface in the material as a whole, which harks us back to Wilson's views of hardness as being dependent on the sort of theoretical framework that you're interested in when you're investigating the hardness of a material. In the same way, surfaces are going to be dependent. What counts as a surface, what you want a surface to do, how you understand what a surface is dependent on the context that you're asking about, and that context is in turn dependent on the scale of the material that you're investigating. That's the story that I like to tell the philosophers. So if you're a philosopher, I just told that story to you. And if you're not, you just got a little bonus, right? So bringing it back to our conversation about classifying nanomaterials, what comes out of this view of nanomaterials as dependent not only on composition, but on size and shape and surface chemistry is the idea that the details of the things that count as structure and the relationships between structures and properties change. We add on to them. We have different ones that we're interested in relative to the structures and properties that we're interested in chemistry. But the structure property paradigm still holds. It's still structural features of the surface that are going to give rise to both to the stabilizing action of capping agents and nanomaterials, and then also to the electronic properties that we're interested in, whether they're, the optical electronic properties. So composition and surface chemistry, we actually see them go back into these notions of chemical microstructure. I showed you chemical microstructural pictures of surface action in chemistry, or in nanomaterials, excuse me. Dimension and shape I call geometric structural features of nanomaterials, in the same way that we can count things like bond angles and bond geometries as geometric structural features of molecules. So like the hexagon that you can see here is a hexagon that's a structural feature of a chemical material. And this tetrad, I think, is used to explain most of the nanomaterial physical and chemical properties that we might be interested in. So bringing it back to gold, what we found is that scale constrains our classificatory interests in nanoscience at least as much as structure, and in a different way than structure, right? Our macroscopic lump of gold has certain properties that are not repeated by our gold nanoparticles, that are not repeated by our individual atoms. These cases are different kinds of kinds. Nanoscale kinds are different than macroscale kinds, are different than atomic kinds, subsisting on different length and time scales. But in each case, the structure property paradigm holds. And I didn't really discuss this much for this case, but you're just going to have to trust me that electronic symmetries are structural. You can tell because I use the word symmetry. So there's a methodological upshot here, that classification issues are intimately tied up with conceptual issues, which I think is why we care about classification so much in philosophy. Philosophy cares about concepts. And so we might ask something like, why do we hold on to surface concepts from bulk materials science when we're trying to classify nanomaterials? And again, I have these same questions from our discussion of nanoscale surfaces. I want to close out.
So
You already saw these.
So what are the concepts from bulk material science, the description of surfaces that we hold on to when we talk about surfaces of nanomaterials?
Well, talking about the surface itself, talking about things like surface curvature and whether or not we would want to use that to describe any of the properties of the material that we're interested in.
You mean on a nanoscale?
Yeah.
Curvature of surface is extremely important.
Yeah.
But
Which is a bulk material concept.
You were saying Why hold on to surface concept from bulk material science?
Yeah.
And I'm asking which concepts are you questioning that we hold on to?
Curvature.
He's
For
asking
example.
Oh,
what
okay,
questions
so
we-
you're answering we need to.
Yes.
All right.
Yes.
okay.
Answering in the affirmative.
Well, because other specific concepts that we don't hold on to besides curvature, but that's okay.
Yeah. No, I mean, so I'm not giving you a catalog of all of the things that might happen to our surface concepts. I'm saying that there are instances where we're going to make use of bulk concepts, and there are instances where we're going to dispense with bulk concepts. And it's a function of scale that we have to pay more attention to and eliminate some of those uses, or question some of those uses, or give individualized justifications of some of those uses, right? Especially when we get to the point where the surface itself is playing a very different role in the material than it is in the macroscopic material. Okay, so I'm going to do a similar thing with alloy just to close out here and give us a transition to the next talk. So alloys, multiple metal compounds. I want to look at steel. This is the man of steel. So let's look at what he's made of. He is made of a combination of iron and carbon in various proportions. And we can look at the structure of steel as it varies across scales. So at the macro scale, at the scale of computers and people, steel is homogeneous. We look at it, it has one color. It's not like this jacket where I can stare at it from up here and I can see a few different colors in the fibers. Steel is relatively homogeneous. It has a single individual melting point for any instance of steel, and different variations, different brands of steel are going to have slightly different melting points. That's a different story. It has something like an elastic modulus, an individual hardness for a given piece of steel. Actually, it occurs to me now that might be one of our destructive classification conversations for later. I can zoom in and I can look at the structural features at a variety of different scales. I'm going to call them the two mesoscales, the in-between scales. I can have arrangements of the pieces of steel that look like a lot of structure, lamellar structure, globular structure, rod-like structure. And I can zoom in on those and I can get even more structures, things like the individual grain structures of steel, bainite and martensite and austenite and ferrite. And if I zoom in even farther, I have just a couple allotropes, which we heard about allotropes yesterday. As a reminder, allotropes, same elemental identities, different structural arrangements. So I can have alpha iron, gamma iron, delta iron. This is where, if I had made these slides slightly earlier, I would have gone back and turned those into Greek alphabet. So you're going to have to read along as if they were the Greek alphabet and not the American alphabet, English alphabet, whatever that one is, the Helvetica alphabet. And so we have graphite as an allotrope, right? So at the crystalline level, we have a couple structures. We have more structures in our intermediate levels. They zoom up and become relatively homogeneous. Right. The reason that I care about this is because I can ask the question of what happens to all of these structures. Do I repeat these structural features at the nanoscale? What happens when I get to nanoscale alloys? What are multi-metal compounds of the nanoscale? Are they alloys? Are they something else? Well, our typical alloy grains are martensite or ferrite or cementite, are often many micrometers long. And micrometers, for those of you playing the home game, are much bigger than nanometers. So when we have something like a grain at the nanoscale, what is it doing that is like a grain at the macroscopic scale? Is it the same sort of thing, just zoomed down? Do I have a different set of structures and behaviors that I'm trying to model? Can I and should I hold on to the concept of a grain in my nanoscale alloys? That's one of the questions that I'm interested in that I've been working on for the past couple of months. It's worth mentioning, and I'll mention it quickly because Evan's letting me know that I'm over time. Not that, Evan.
Since you point at me, what about like holes where you have little cavities or other localized structures
Yeah.
that may or may not be regular, however critical for the activity and function of the nanomaterial.
Yeah, what about them? It's a good question, right? So we have intermetallics, which function more like crystals at the nanoscale. These are sort of reliable, repeatable structures in a way that regular old alloys wouldn't be.
So what's your answer? How do we understand?
It's going to be similar to the surface
Do you
answer.
think grains are appropriate to?
Sometimes, yeah. So here, I'll zoom ahead and tell you, I think that's a grain, right? I think that there are times when, and this is actually from one of Michael's papers that we may hear about in a little bit, there are times when an individual atom in a nanoscale alloy can behave like a grain in that it changes the electronic structure, it changes the properties that we care about. There are times when we want to preserve the idea of amorphous or malleable structural features that we associate with grains and macroscopic alloys. And then there are times when we want to abandon the grain concept entirely and talk about a single lattice structure in an intermetallic at the nanoscale.
Problem of identifying individual phases within a nanomaterial.
Yeah.
Yeah, but that's, okay, keep going.
Yeah. So I skipped a slide, but I'm just going to let that be skipped. To answer John's question in a little bit more detail, I think that there are times when we want to hold on to the alloy concept in nanomaterials. In order to do so, we need to extend the concept of an alloy and the associated concepts beyond their original domains. But doing so can suggest certain sorts of experiments and modeling strategies. If we're not thinking of that individual heteroatom as a grain, if we're thinking of it just as a heteroatom with electronic symmetries, it's going to suggest a certain sort of experiments. If we're thinking of it as a grain and we're thinking of any individual atom in an alloy, in a nanomaterial, as a grain structure, it's going to suggest a way of treating the material that's different than thinking of it as an atomic or molecular material. So like I said, heteroatoms and nanomaterials can impact physical properties. And like our mesostructure, like grains, the distribution of these heteroatoms can impact physical properties, whereas we wouldn't think of distribution of heteroatoms as a molecular feature, because if we're thinking molecularly, structure is always the same. And then, like with the story of surfaces, we need to think about when these analogies, where are the limits of applicability of importing this alloy concept into the nanoscale. So just to summarize quickly, Section 1, the methodological problem of kinds lies at the heart of philosophy of science's interests in kinds. Section 2, the methodological study of chemical kinds reveals the structure property paradigm. Section 3, first start of Section 3, the structure property paradigm rationalizes the distinction between chemical and nanoscale classification. And then the last two sections, investigating surface chemistry and alloying behavior, shows scale-dependent changes in material properties, which we're going to need to understand before we classify these things. So I just want to take a couple minutes quickly to thank people who've been involved in this project. The Department of Philosophy here, and Jen Waller, who's our department admin. Most of you have gotten many emails from her. She has been invaluable to this workshop, and I don't think I mentioned her by name yesterday, so I just wanted to make sure that we got that out there. Thanks to you guys. Thanks to the NSF for supporting this when I was a graduate student. I'm going to leave it there. I got plenty along the way.
Or we can come back, but.
Okay, I just have a quick one. Have you thought about supervenience as a relation, or emergence as a relation between the structure property thing? So maybe like a little bit of detail.
So I see scale dependence as an alternative both to reduction and to emergence or supervenience. For me, the thing that emergence and supervenience gets wrong. So let's dig out of the weeds of philosophy for a second here. Reduction in philosophy is the story that for any theory we can back it down to physics eventually. And all of the interesting relations are physical relations, and all of our stories about psychological properties, chemical properties, biological properties are sort of complicated shorthand for physical properties. And we have them because we are human beings of limited cognitive capacities, but all they're doing is capturing very complicated physical properties in ways that our limited human minds can cognize. That's the reductive story. The emergent story is the counterpart to that in that it says, no, there genuinely are biological features of the world, psychological features of the world, neurological features of the world that are not just physical features writ complicated, right? There are things that don't reduce to physics that we really care about in the sciences. Chemistry is always an interesting, has an interesting role to play in these debates because chemistry is like the next step up from physics in a lot of these stories. But I think there's a thing that both reductive and emergent approaches to inter-theory relations get somewhat wrong, which is to think of there being a hierarchy in the first place. I think, emergence rejects the idea that the hierarchy is going to reduce down, but still acknowledges that there's a hierarchy of generality there in the first place. And what scale dependence gets us is a different lens to investigate the relationships among the phenomena. Can you let our last speaker in? Thanks. Yeah.
Yeah, that's the impression that I got.
Well, so even if you don't sort of reduce things or use emergence, I mean, have you ever thought about dynamical relations between the scales? I mean, physicists do that all the time, right?
Yeah.
Rather than discrete properties.
Totally fine with that. Yeah.
All right, that's an optimistic note on which to move on to our next talk. But first, let's once more